In most cases, light can oscillate in any and all directions. In these cases, light is said to be unpolarized. However, it is possible to filter light in such a way that it is allowed to oscillate in only one direction. This is called the process of polarization.
Let's talk a little bit about what polarization means. Natural light is generally unpolarized. Unpolarized light is when the electric field vector of the light wave fluctuates randomly in time. However, if the direction vector of the electric field is well defined, the light is said to be polarized. There are three main types of polarization. Linear polarization is when the electric field vector is confined to a given plane along the direction of propagation. Polarizing sunglasses use linear polarization to reduce glare. When sunlight reflects off the ground, the light is generally polarized parallel to the plane of incidence, essentially horizontally. These rays bundle up and is what leads to a glare. Polarized sunglasses are polarizers that only allow vertically polarized light through, and in doing so reduces the glare. Circularly polarized light consists of two perpendicular electromagnetic plane waves of equal amplitude and 90-degree difference in phase. And so the electric field vector seems to be traveling in a circular motion to an observer watching the wave propagate. Elliptically polarized light is the general case of circular polarization and consists of two perpendicular waves of unequal amplitude and with a random phase difference.
Let's talk about methods of polarization. The first one, reflection. When light meets boundary between two media, part of it is reflected and part of it is refracted. We can calculate the angle of reflection and refraction using Snell's law. It turns out that when the incident light comes at a certain angle, so that the angle between the reflected and refracted light is 90 degrees, the reflected light is totally polarized. That is, the electric field oscillates only in the direction parallel to the interface between the two media.
In this particular situation, the angle of incidence and the angle of reflection are called Brewster's angle. Let's see how we can find Brewster's angle. We can see from the diagram that the sum of Brewster's angle and the angle of refraction must be pi over 2 or 90 degrees. By rearranging, the refracted angle is pi over 2 minus Brewster's angle. We can substitute the sine expression for the cosine of Brewster's angle. This is because the two are trigonometrically equivalent. We will now use this expression in the right-hand side of Snell's law. This allows us to have the whole expression in terms of Brewster's angle. By dividing through and rearranging, we get that the tan of Brewster's angle is equal to n2 over n1.
A second method of polarization is by absorption. The method is used in sunglasses and Polaroid film. It is based on this property of some crystalline materials, called derive, that some atoms absorb more light in the direction parallel to the long molecules in the crystal by creating oscillations. Therefore, the crystal acts as a polarizer. Polarization by scattering. Let us imagine a molecule or an atom upon which light is incident. The atom or molecule will absorb the light and re-emit it in various directions, phenomena called scattering. After the scattering, light is completely polarized, perpendicular to the incident wave. Unpolarized if the direction is parallel to the incident wave, and partially polarized at all the other directions.
Let's start deriving Malus's law with this diagram. Here we have unpolarized light approaching a polarizing filter. The light is oscillating in all directions until it passes through the polarizer, which only lets light oscillating in one vertical plane through. Next, let's say it approaches another polarizing filter, this time tilted through an angle theta. We can already say that if the two filters were aligned so that they were parallel, all the light allowed past the first filter would also be allowed past the second. We also know that if the second was tilted through 90 degrees, so that they were perpendicular, all of the light would be blocked. Therefore, we can start writing an equation to show this, where the final amplitude A is equal to the original amplitude, A0, multiplied by cos theta. We can check this with the ideas we previously discussed. If theta is 0, so the filters are parallel, cos theta would be 1 and A would equal A0. If theta is 90, so that the polarizers are perpendicular, cos theta would be 0 and the final amplitude would also be 0. When talking about polarization, we generally think in terms of intensity and not amplitude, but it's really easy to modify our equation just by knowing that intensity is directly proportional to amplitude squared. So now let's just square everything and our equation becomes a squared equals a0 squared cos squared theta. And now all we have to do is replace all the amplitude squared terms with intensities. So finally we get I equals I naught cos squared theta, and this is Malus's law.
We hope you enjoyed this video. Remember to like, share, subscribe, and comment your ideas for our next video down below.